So I'm going to go briefly over a little bit of the business that I do, so you would perhaps know a little bit more about where I'm coming from. I got involved in remote sensing by studying the use of various passive microwave techniques, and in particular applied to Earth remote sensing. And when we speak about Earth remote sensing, one of the biggest factors that affects us in being able to apply microwave techniques is the transmission of microwave energy through the atmosphere. And that transmission is variable depending upon what frequency one works at. So one works at a very low frequency, below about 2 gigahertz or so, the atmosphere is virtually transparent. One really doesn't need to worry too much about it, unless, of course, you go low enough in frequency where we have ionospheric effects. When you start going up to higher frequencies, though, you start finding that there are particular places in the spectrum where there are strong absorption features. And these absorption features go from just about nothing from the standpoint of practical application, practical impact, all the way to zenith opacities. In other words, the attenuation from the surface on up to the top of the atmosphere in decibels that approach almost 1 million decibels. Not quite 1 million. There are some places a little bit further up the spectrum that are about that. 1 million decibels, mind you. Now, 10 decibels is a factor of 10 loss in power. 20 decibels is a factor of 100 loss in power. 30 decibels is a factor of 1,000 loss in power. There are places in the atmosphere where we have hundreds of thousands of decibels of loss. In other words, that wave penetrates perhaps only a fraction of a millimeter. And so what we have is really an extremely rich spectrum of transmission throughout this range from, again, RF, on the order of a gigahertz or so, on up to the terahertz range, where we can get propagation distances that are effectively all through the atmosphere, no attenuation whatsoever, all the way to propagation of perhaps no more than 1 millimeter or so. This is one of the things that got me excited about remote sensing. There's really a tremendous amount of structure in this atmospheric absorption spectrum. And there are a lot of things you can do with it as well. I'm just going to briefly allude to some of them, and I'll show you some slides. But as we go around the exterior of this slide, we can see some of them. We can, if we look at low enough frequencies, see all the way through the atmosphere, all the way through clouds, have no effect of weather upon us at all. And in fact, we can see down into the soil and measure the amount of moisture in the soil. And we can do that at frequencies typically below 10 gigahertz. There are some preferred frequencies around 1.5 gigahertz for various reasons, 1.4 gigahertz actually. But it turns out that this system can be used to map the moisture throughout the globe, which changes on a daily basis, even as there's rain deposited, as there's evaporation, etc. We can also, if we go a little bit higher in frequency, we can measure very clearly the temperature of the ocean surface. And this is a map of ocean surface temperature. Turns out this is also the temperature in the first roughly couple of millimeters of the ocean. So we're actually probing down just a little bit into the skin of the ocean, starting to measure the bulk temperature in the ocean. And we can do this through clouds day and night, because the clouds don't affect us, because this is basically a thermal signature. And here's a great example of exactly that. This little cold spot here is actually the wake of Hurricane Katrina. You recall Hurricane Katrina devastated New Orleans, very serious event. Well, that event was powered by something. It was powered by heat in the ocean. That's, of course, what people commonly say. Of course, hurricanes are powered by heat in the ocean. Well, here is direct evidence of it. As that hurricane passed over the Gulf of Mexico, it actually left cold water in its path. And this is perfect evidence of the fact that these engines, these huge, rather destructive engines, are driven by heat in the ocean. Again, these are things that you couldn't see without some kind of remote sensing technique, and here we've arrived at a very good technique for doing that. We can also measure the direction of winds on the ocean surface. Each of these little flags is a wind barb, and it shows us not only the direction but also the speed of the wind at the ocean surface. This is extremely important for meteorological forecasting. If there's one variable in meteorology that's significant from the standpoint of forecasting, it is wind, and in particular wind direction, because that tells you what direction all the mass in the atmosphere happens to be moving at any one time. We can do that with certain microwave frequencies. Here, with other microwave frequencies, we can measure the amount of water vapor in the atmosphere. And you can see down here in the tropics, this is where we get most of our solar flux absorbed. We have a lot of water vapor being generated. Of course, if any of you have been down in the tropics, you know it's very humid. But on the other hand, that humidity also makes its way up to our latitudes, our mid-latitudes, and it does so by rather interesting mechanisms. And what you can see here in this time lapse is one of these rather important mechanisms. It's a mechanism called a low-level jet, also known as an atmospheric river. And what happens is we have cold fronts coming down from the north. We have a very moist atmosphere down here. And because we have essentially a lower pressure in these cold fronts and a higher pressure in this warmer region, the Coriolis force drives moisture along the front of that boundary. And that moisture impacts the continents, and it deposits a great deal, not all, but a great deal of the moisture that we actually receive in the form of rain and snow. In fact, if you look at the flux of water vapor, the amount of water vapor in terms of kilograms per meter squared, integrated across the front of that event, what you find out is that this water is approximately comparable at any one time to the outflow of the Mississippi River. There's that much moisture, in other words, that is coming from the tropics over to our mid-latitudes. But when you think about it, that stands to reason, too. Because if you have that much moisture flowing out, you've got to have that much moisture flowing in somehow. These kind of features, these meteorological features, were not even discussed until roughly the 1980s. They weren't observed until roughly the middle of the 1990s. And now we know how to not only observe them quite well, but also forecast them by knowing what many of the fields are that are important here. The moisture fields, the temperature fields, the wind fields, etc. And again, this is all through remote sensing. A lot of other things we can do. We can measure snow water equivalent, the amount of snow that's on the ground, which has a lot to do with the reflection of sunlight, with the amount of storage of water. We can measure the amount of temperature in the atmosphere. Again, by passive means, we're really measuring the amount of thermal emission coming from the atmosphere, and if we're clever about working at just the right microwave frequency, we can determine from where that emission comes, and therefore what the temperature is as a function of height. And this is a technique called atmospheric sounding. So we can actually measure the temperature profile of the Earth's atmosphere, or any planetary atmosphere, through this sounding technique. We can also measure sea ice fraction, which is very important. Sea ice has a great deal of change in emissivity relative to open water. And so as we look down on the planet from satellites, that sea ice reflects very much differently. It actually appears warmer, ironically, than the sea does. It turns out seawater reflects the cold background. The ice appears warmer. And as a result of that, we can map the amount of ice on the poles. And mapping that ice through clouds 24 hours a day is a very valuable technique in understanding how climate is impacting changes in the ice in the polar caps. And as you all should know, it's impacting it quite significantly. There's been a long historic trend of ice loss that is continuing rather rapidly, and we expect that sometime in the next perhaps several decades we may see a summer without any sea ice in the Arctic. Precipitation is also able to be measured. This is using a radar now. This is the so-called Tropical Rainfall Measurement Mission. It's a satellite that's been operating for 14 years now, using both a radar and a radiometer. And this is the result of the radar measurement on a daily basis. It measures precipitation over a lot of the globe. This mission is being extended now to cover the entire globe.